Hello, today we are going to discuss Raman spectra under atomic molecular physics. So let us get started. So we will briefly discuss what is Raman spectra and we will do around 3 problems. So what is Raman spectra? Raman spectra is, Raman spectra is observed when light of particular frequency falls on a medium and then we observe the scattered light. So scattered light can be because of 2 reasons. One is elastic scattering, where the frequency of the light does not change, and inelastic scattering, that is the frequency of the light changes. So we have 2 kinds. One is the Stokes and one is the anti-Stokes. Stokes will have a frequency less than the frequency of the light that excites the medium, and anti-Stokes will have frequency of the photon which is greater than the frequency that excites the medium. And what is another important thing is that the molecule will have a dipole moment and the polarizability of the molecule will vary with time. So there is a variation of polarizability with time. And so the spectra consists of information about the rotational and the vibrational degrees of freedom of the medium. So this is how it looks like. So this is the Rayleigh line. So this is due to elastic scattering, and then the red lines are the transitions between the vibrational levels. So this is a Stokes line which is having a lesser frequency, the red one, and we have the anti-Stokes line. And associated with each red line we have even fine structures which are due to the transitions between the rotational levels of the molecule. So these blue lines represent the rotational spectrum. So here associated with Rayleigh line we have rotational spectrum, and with anti-Stokes also we have rotational spectrum. And the selection rule is delta n, that is change in the vibration quantum number, should be plus minus 1, and delta j, that is the change in the rotational quantum number, should be 0 or plus minus 2. So we can see here. So what is important here is that, here we have 2 vibrational levels, n is equal to 0 and n is equal to 1, and we have a virtual state. So this virtual state is important. So this is called virtual because this state is not intrinsic to the molecule. It forms only for a very, very short period of amount of time when the light or the photon interacts with the molecule. So this is called a virtual state. So all these transitions involve virtual state. So in the red line we have, so red line denotes Rayleigh scattering. So from n is equal to 0 state, the molecule goes to the virtual state and again falls back to the n is equal to 0 state. So no change in energy. So this line, so this is what is observed. So this has no change in frequency, is called the Rayleigh line. And if you go to the blue line, so the blue line denotes the Stokes. Stokes means, so say from n is equal to 0, the molecule goes to the virtual state and then again it falls back to n is equal to 1 state. So basically, so this is the line that is observed in the spectrum. So this has a lesser frequency than the Rayleigh. Okay, so this is called the Stokes, and we have anti-Stokes, that is, suppose from n is equal to 1, the molecule is excited to the virtual state, and then it falls back to n is equal to 0. So this line is emitted. So this is what we see in the spectrum, and this has a larger frequency than the Rayleigh line, and this is called the anti-Stokes, which has a higher frequency. So that is how it is, anti-Stokes. So this has a high frequency. This one has the same frequency as the incident light, and this one has a lesser frequency. And then associated with it, we have the even final lines linked to the rotational spectrum. So how does it happen? So suppose we are here. So this, say here, then what happens? So effectively, so these are the rotational levels. J is equal to 0, 1, 2. So these are the rotational levels. Okay. And so what happens is, say in that same vibrational level, there is effectively a transition from, say, J is equal to 0. So J is equal to 0, from this to J is equal to 2. So the molecule goes to a higher level. So effectively, the emitted line has a lesser frequency, and this emitted light is given by this yellow line. Okay? Or a molecule can go from, say, J is equal to 1 to J is equal to 3 in the same vibration level, effectively. Because all these transitions are taking place via the virtual state. So it goes to the virtual state and then falls back. So from J is equal to 2, it goes to the virtual state, and then it falls back to J is equal to 3. So effectively, the molecule is excited from J is equal to 0, J is equal to 1 to J is equal to 3 state, and corresponding to that, the wavelength or energy that is, or the line that is emitted, is given by this yellow line. So that is how it happens. Or it may happen that from J is equal to 2, the molecule de-excites to a lower energy level, J is equal to 0. So in that case, the emitted spectrum, the emitted line has a larger frequency, and here it is given by this. So this is an effective transition from J is equal to 0 to J is equal to 2 to J is equal to 0. And all the transitions are going through your virtual state. Or you can have a transition from J is equal to 2 to J is equal to 0, or you can have a transition from J is equal to 3 to, J is equal to 1. So this transition you can have. So this transition is given by this. So this transition effectively will emit a frequency which is higher than the incident frequency, and this is the central line, and to the left and the right we have the transitions between the rotational levels. So it is like this here. So we talked about this spectrum. We can similarly talk about this spectrum also, or this spectrum. So in that case, what happens? These transitions are, say, J is equal to 0 belongs to one particular vibrational level, and J is equal to 2 belongs to another vibrational level. So effectively, the molecule is excited from J is equal to 0 of one vibration level to J is equal to another vibration level. Okay, so it could explain this kind of line, this part of the spectrum. So we have this central line, and to the left and right we have the smaller lines associated with the rotational degrees of freedom. Similarly, you can explain this line also, anti-Stokes. In that case, here, say J is equal to 3 will be the initial vibrational rotational state in the initial vibrational state, and J is equal to 1 will be the final vibrational final rotation state in the final vibrational level, and that will give us this line. So this is the spacing between them can be easily found out. So this is the central line, and the first Stokes line, rotational Stokes line or anti-Stokes line, the difference between these is 6B. To the second Stokes line has a difference of 10B. Okay, so the difference between the first and the second anti-Stokes is 4B, and the difference between the first and the second Stokes is 4B. So this is Fj is equal to Bj into J plus 1. So this we know. So this is related to the energy. So this is energy or frequency of a particular level, rotational level, and this is expressed in terms of inverse length. This thing we have done before, and we have defined what is B also. So Fj is Bj into J plus 1. So delta Fj is equal to Fj plus 2 minus Fj, and that you can see easily comes out to be B into 4J plus 6. So now delta F0, that is J is equal to 0, comes out to be 6B. Delta F1 comes out to be 10B. Delta F2 comes out to be 14B, and that is what we have written here. 6B, 6B, and then 10B, 10B, like that. So here we are only interested in the changes between the rotational levels, and the change in the vibration level is given by this line, or the vibrational quantum number. So let us do a few problems. So in a spectrum resulting from Raman scattering, IR denotes the intensity of Rayleigh scattering. IS and IAS denote the most intense Stokes and the most intense anti-Stokes line. Then which of the following is true? Intensity of Stokes is greater than intensity of Rayleigh, greater than intensity of anti-Stokes, etc. So we have 4 options. Always remember that Stokes line, you can see from here that the Stokes line, the blue one, the excitation is from a lower energy level, and say at a low temperature, the lower energy level is having the highest population compared to higher energy states. So you can see that most of the molecules will be in the ground state, and that is why the Stokes line will have the maximum intensity, will have a greater intensity compared to the anti-Stokes line, because anti-Stokes, the transition takes place from a higher state, higher vibrational state to the virtual state. So this will be less populated, and hence its energy will be lower, and Rayleigh will always have the highest intensity. So the correct answer will be intensity of Rayleigh will be the greatest, then it will be greater than intensity of Stokes, and intensity of Stokes is greater than intensity of anti-Stokes. So this is the correct answer. So so we go to the next problem. So in a next experiment, the exciting line of a sample is observed at 2460 angstrom, and the Stokes line is observed at 2520 angstrom. Show that the wavelength of the anti-Stokes line is almost 2404 angstrom. This is simple. So we are interested in the red lines here, and the difference between them in units of length inverse is the same. So this difference is the same in units of inverse length. So what we can write is 1 by lambda r Rayleigh, wavelength of Rayleigh minus 1 by lambda s, this is Stokes, is equal to 1 by lambda as anti-Stokes minus 1 by lambda r. And lambda r is given, this is lambda r, and lambda s is also given. So we have to find out what is lambda s. So this is straightforward. We go to the next problem. In the rotational Raman spectrum of HCl molecule, the displacements of the exciting line are observed as nu plus minus 180 plus 120 j. J is the rotational quantum number, centimeter inverse. Show that the moment of inertia of the molecule is 9.3 into 10 to the power minus 48 in SI unit. So this is like here, we are interested in purely rotational spectrum. So we are here, this part, and we already know, so nu plus minus this, and we have already obtained, we know this, right, isn't it, this thing, delta Fj is B 4j plus 6, that is what is given here. Okay, the displacements of the exciting line are represented by centimeter inverse in units of centimeter, in units of 1 by length. So we convert this into meter inverse. So what we get is delta Fj is equal to B into 4j plus 6, that we know, and this is my delta Fj, this part. So comparing, we get what is the value of B after converting this into meter inverse, and once I know B, I know the actual expression for B, is it not? This is h by 8 pi square I, which is moment of inertia, into c. So from here we can calculate what is I. Okay, and it should come out to be this. We go to the final problem. The first line in the rotation spectrum of a diatomic molecule appears with a Stokes shift of 24 centimeter inverse. Stokes shift means it has a lesser frequency shift, and the Stokes shift for the third line is, you have to fill in the blanks, what will be here. So the first Stokes shift we know, we have seen here, happens at 6b. Okay, it happens at 6b. 6b is equal to 24, and then the third line is, what is the Stokes shift of the third line? Third line will be first, second, third. So 6 plus 10, 4, and this one be also 4b, so it will be 14b. So 14b, so we have to find out what is 14b, and from here it's trivial. So we can find out what is 14b, and it should come out to be 56. So we end here. We'll meet in the next lecture, maybe with laser, lecture on laser. So thank you.